systems. LTI means a system is both linear and time invariant. A system that satisfies both these conditions, linearity property and time invariance property. If a system satisfies both these conditions, then we can say that the system is a linear time invariant system. We'll be discussing only about this linear time invariant system in this course. The reason is that most of the practical systems can be well approximated by this LTI model. Now, when we analyze these systems, a linear time invariant system, it is the analysis is simplified if we can suppose we want to find the output corresponding to a signal xt. It is a complex so the shape is it is not a simple signal, some complex signal. It is not complex valued, I am talking about the shape. Okay, some signal xt, and you want to find the output corresponding to that signal, and that is the analysis problem. That analysis is greatly simplified if we can express this signal xt as a linear combination of some basic signals. Okay, if we can express this complex signal as a linear combination of some basic signals. Basic signal means xit to, let's say, if xit is the input, yit is the output. Let us consider let's say this is I is from 1 to n. That means in this case we are expressing this signal xt as a linear combination of n basic signals. Basic signal in the sense finding this finding the output corresponding to this basic signal is very easy. Okay, we'll discuss about that later on, but how to find that basic signals. But if the if analyzing this the system for this basic signal as the input, if it is easy, then we can easily find the output corresponding to a complex signal using the linearity property. Is it? That analysis will be greatly simplified if we can decompose it as a linear, if we can express it as a linear combination of some basic signals, and if we can find the output corresponding to this basic signal very easily, then we can that analysis problem will be simplified. It can be further simplified if this xit, let's say I'm simply writing this. What does it mean? We have some signal x naught t. Okay, it's a simple signal x naught t. If all these components of this signal xt, if all these can be expressed as a shifted version of that basic signal x naught t, then in terms of this, how can we express this input signal? Can we write it as a into x naught t minus, let's say, some constant ni? This is a constant. That means it is a shifted version of some basic signal. What will be the output? Okay, let me write it here. Sigma I into x naught t minus ni. Okay. We are expressing a signal xt as a linear combination of this. Then what will be the output using the linearity property? What is the output if x naught t output is y naught t? What will be the output corresponding to this x naught t minus ni? What will be the output corresponding to this? If the output corresponding to the signal x naught t is y naught t, and we are given
Y
the
not t
information
minus
that
ni.
system is both linear and time invariant. So using the time invariance property, we can write it as y naught t minus ni. Is it that? Now tell me, what is the output corresponding to this? I have to erase few things. Where is the erase? Okay, tell me, I'm writing it here. Summation I ai x naught t minus ni. What is the meaning of this? We are writing a signal xt as a linear combination of what? Linear combination of what is this? We have a basic signal x naught t. We are expressing a signal xt as a linear combination of what about this? What is it called? Is it time shifted version of this x naught t?
Yes, sir.
Yes, sir.
So what we are doing here is we are expressing any signal as a linear combination of time shifted version of a basic signal. Now tell me, what will be the output?
Summation ai y naught t minus ni.
Y naught t minus ni. Is it? Now we have a basic signal x naught t, and if we can easily find the output corresponding to that, can we get the answer directly? If we know this and these coefficients, then can we get this directly? Does it simplify
Yes,
the
sir.
analysis? So what we are doing here is, given a complex signal, we are expressing it as a linear combination of some basic signal, shifted versions of some basic signal, and we are trying to find the output corresponding to that signal. So what I am saying here is, if we can find the output corresponding to this basic signal easily, then we can directly get the output, isn't it? Because the output is a linear combination of shifted version of this y naught t. If we know these coefficients, we can directly get the output. Is it that?
Yes, sir.
Yes.
Okay. So that will greatly simplify the analysis. Now the question is how to find this decomposition. How to find this basics. How to find a basic signal such that whatever signal you are giving, it can be expressed as a linear combination of shifted version of that basic signal. Is there any such signal?
So sinusoidal signal.
Sinusoidal signal. Okay. Sinusoidal signal, we'll come back to that later. We'll discuss about that later. Now let us start with a discrete time system. I am considering a discrete time system because first we will start with the discrete time system and then we'll move on to continuous time system. Okay, because that is easy approach. It is easy to prove in the discrete time signals. If you are given a signal xn, let's say let us assume that there are only three non-zero values. Okay. These are the values. Now can we write it as I'm drawing only one non-zero value. This is a signal having only one non-zero value. Okay. Okay. Let us take this also as let's say this as 0.5, and so this is 0.5, 2, 3. Is this sum of these three signals?
Yes,
We
sir.
are considering a discrete time signal, let's say xn. It is having three non-zero values. X0 is 0.5, x1 is 2, x2 is 3. Now I am writing it as sum of these three signals. Now can you tell me what is this signal? What is the expression for that signal?
Half times Q
Half is what? Is it
delta.
x0? x0?
Yes, sir.
Is it x0 or x0 into delta n?
Delta n.
Then only x0 is a constant. This is a function. It is x0 into delta n. Now what about this?
So x1 into delta n minus 1.
It is x1 into delta n minus 1. Then this one is
x2 into delta n minus 1.
x2 into delta n minus 2. Okay. Now what are we doing here? We are writing xn as a linear combination of what? Linear combination of delta n minus 1, delta n minus 2. Is it that?
Yes, sir.
So can we say that we are expressing a signal xn as a linear combination of shifted delta functions? Is it that?
Yes, sir.
We are expressing any signal, a given signal, as a linear combination of shifted delta functions. Now, can we generalize this? Here I am considering only two values and assuming that other values are 0. Can we generalize this? Xn is summation k from minus infinity to infinity. If we consider all the values of x, then what will be the expression?
Xk delta n minus k.
It is xk delta n minus k. Is it this? So given any signal, given any discrete time signal xn, we can express it as a linear combination of shifted delta functions. Is it true? Now, what is this summation? You must have studied this summation before. But is summation? This has got a special name. What is that summation?
Convolution.
It is the convolution summation. Is it? How do we define the convolution summation? If you consider two discrete sequences, let's say x1n and x2n, the convolution of these two, the x1n and x2n, the standard notation is this. This is the notation for convolution operation. It is defined as summation that is convolution operation. Okay. What we have shown here is if you are given any discrete time signal, we can express it as a linear combination of okay, this is what we have seen. Now, if we want to give xn as the input to an LTI system, okay, if we want to give a xt as the input to the to an LTI system, and you want to find the output yn, can we use this decomposition to simplify that analysis?
Yes, sir.
Okay, we know xn. So what else do we need to know? What is the output corresponding to this? Okay, if I am writing, if you are giving delta n as the input to the system, you are given an LTI system and giving impulse delta n as the input. There is a standard notation for this. It is denoted by hn. It is called the impulse response of the system. Impulse response. Okay. Impulse response means the output when the input is an impulse. This is a discrete time impulse function or Dirac delta function. That is called the impulse response of the system. Now, if we know this impulse response, can you find the output corresponding? What will be the output in terms of this Hn? If this is the input to the system, what will be the output using linearity and time invariance property?
Summation xk h of n minus k.
Xk h of n minus k, isn't it? We are using both linearity and time invariance property here. So if we, and what is this summation? Is it convolution? Is it convolution? Yes or no?
Yes, sir.
This is convolution of what? Xn and okay, so yn is, so only thing we need to know is this. Is it? If we, so can we say that if we know the impulse response of a system, we can find the output corresponding to any input xn. We don't need to know anything else, only the impulse response. If we know the impulse response, we can find the output corresponding to any input. If the system is linear time invariant, is it true? This is the relation. Yn is xn, that is the given input signal. If we know the impulse response of that system, just take the convolution of that input signal, just convolve that input signal and the impulse response, you will get the output signal. This is convolution summation. Now let us see what happens in the case of a continuous time system. We are writing a signal x and we are expressing a signal as we started from here, expressing a signal as a linear combination of shifted delta functions. Now what happens in the, let us see what happens in the case of continuous time signal. We have a signal xt and we can easily prove that instead of summation, it is a integration. Okay, this is a relation. How can we prove this? The right hand side is equal to the left hand side. This is integration with respect to tau. So both are function of tau. So with respect to that integration, this t is a constant. Now what about this function? When will this be non-zero? Delta t minus tau. What is the property of delta function? When is this?
equal to tau.
Sorry?
70 is equal to tau.
When t is equal to tau. Or here tau is the variable. So we can say that when tau is equal to t, then it is non-zero, and for all other values of tau it is 0, because here we are considering tau as the variable. So can we write this as integral minus infinity to infinity xt delta t minus tau d tau? Is it that? Because this function is non-zero only when tau is equal to t. So here this one. Now since the integration is with respect to tau, we can take this outside the summation. So it is xt integral minus infinity to infinity delta t minus tau d tau. What is that integral? What is this?
1.
It is area under an impulse, isn't it? Area under a shifted impulse, it is 1. So this is xt. Okay. So we can write xt is equal to xt convolution delta t. Okay. And convolution integral for continuous time signals, it is defined as convolution of two signals x1t and x2t, that is defined as integral minus infinity to infinity x1 tau x2 t minus tau d tau. This is a definition of convolution integral. Today let us discuss about the output corresponding to how we can express the output of a linear time invariant system in terms of its impulse response. Okay, so we have a system, LTI system, continuous time LTI system. Its input is xt. That means we are giving because xt is equal to integral minus infinity to infinity x tau delta t minus tau d tau. That is the input to that system. And what is the output? Using the linearity property and time invariance property, how to find the output of that system. Okay, for this this integral, let us consider a function. I am considering a function f tau. Okay, let the function be something like this. Now, if we want to find the area under this function, integral minus infinity to infinity f tau d tau, you must have studied the Riemann summation, isn't it? Have you studied that Riemann summation? Yes?
Yes, sir.
Sorry?
Yes, sir.
You have studied that, isn't it? What is that Riemann summation? We can break up this integration into like small rectangular pulses. Let me take a different color. Okay, I'm taking considering, let's say, width of this pulse is delta. Now, what is the area under this pulse? This part? If this is f tau, this is delta. What is the height of this? What is the height of this pulse? What we are doing here is, for finding the area under this function, we find the sum of the, it is approximately the sum of the areas of this rectangular pulses, isn't it? Is it that?
Yes, sir. Sir,
That is,
F0 into delta.
that is the Riemann summation. So now this function, this pulse, can we write it as f0 into, is it f0 into, is this the area? Height is f0 and this is delta. Width is delta. Now what about the second sum? Second area of the second, area under the second pulse? What is the height of that pulse?
F delta.
It is f delta. Okay, delta times f delta, like that. Now what about the negative side? Delta into f minus delta. Is it that? Is it?
Yes.
Yes, sir.
So now we can generalize this. The area, if we add the areas of these rectangular pulses, this is summation k from minus infinity to infinity delta fk delta. Is it that? That is the sum of the area. This sum of the areas of this pulses, isn't it? Rectangular pulses. Now, in the limiting case, limit delta tends to 0. This is equal to what?
The integral.
It is the integral of that function. Okay, that is how we write, we express the integral as a Riemann summation, isn't it? Okay, so let us use this. Now, in terms of Riemann summation, this is the input to our system, isn't it? How can we write this? This is a, can we, if we take f tau is equal to x tau delta t minus tau. Okay, let's say the function f tau is x tau into delta t minus tau. Now, what is the Riemann summation? Is it limit delta tends to 0? What? Limit delta tends to 0? Summation k minus infinity to infinity. What is the term inside that summation? I'm taking, look at this. Here I am taking f tau is x tau into delta t minus tau. Now what is the summation? Is it delta into x k delta t minus k delta? Is it that summation?
Yes, sir.
Yes, sir.
That is a summation, isn't it? Now, if we are giving this as the input to a linear time invariant system, what will be the output? If you are giving this as the input to a linear time invariant system, what will be the output?
XT.
What xt? I'm saying that this summation we are expressing a linear combination of signals as the input to linear time invariant system. What will be the output corresponding to system? Forget about the limiting case. Suppose this summation is given as the input to the linear time invariant system. What will be the output? Suppose we are giving delta t, and let's say the output is denoted by ht, that is called the impulse response of the system. Now, can you tell me what is the output corresponding to this summation, this linear combination? What is this delta? What is the output corresponding to delta t minus k delta?
H of t minus k delta.
It is h of t minus k delta, isn't it? Is it? H of k minus t delta, the output corresponding to this part. So we are writing integral minus infinity to infinity x tau delta t minus tau d tau. That is the input to the system. That is equal to limit delta tends to 0 summation delta into x k delta into delta t minus k delta. Okay, this is a summation, Riemann summation. Now, if you are giving this as the input to the system, the corresponding output will be limit delta tends to 0 delta into xk delta is a constant, the value of that function at that instant of time, and this will be ht minus k delta. Okay, this is, here we are using the property of linear time invariant system. The property we are using is, if we are giving delta t as the input, we will get ht, and if we are giving delta t delayed version of delta function, it will be ht minus t naught. Okay, we are using that property. Now, what will happen in the limiting case as delta tends to 0? What is that
It
integral?
will be integral.
It is integral minus infinity to infinity x tau ht minus tau d tau. That is yt, the output of the system. Okay. So what is this output? Is it the convolution of input signal and the impulse response of the system? This is the convolution integral, isn't it? So we can write yt xt convolution st. Okay. Now what does it mean? If we are given a linear time invariant system, and if you know the impulse response of the system, we can find the output corresponding to any input signal using this convolution integral. We don't need to know anything more about the system, only the impulse response of the system. Then we can find the output corresponding to any signal using the convolution integral. Is it? Is it that?
Yes, sir.
Okay, now tell me, you are given, suppose you are given a system. How to find the impulse response of a system? What is impulse response?
The output of delta function.
That means you have to give delta t as the input, you will get st as the output. So what we have seen here is, if we can find the impulse response, we can find the output corresponding to any system. Now, does this make any sense? Because we are saying that if we can find the output corresponding to delta t, which is not physically realizable, then we know everything about the system. Is it that? How to find the impulse response of a system? Is it possible? You are given a system, generate an impulse, find the output. In the case of continuous time, discrete time system, there is no issue because we can generate the signal delta n. How is it defined? Delta n, Kronecker delta function. How is it defined?
So 1 for n equal to 0.
1 for
Zero.
n equal to 0 and 0 for all the values. So all other values. Okay. Now, in the case of continuous time system, does it make any sense? Like you are saying that if we know the impulse response, which we cannot compute physically, like it is not possible to generate impulse, then how can we find the impulse response of a system? There are different methods we can do that. I will give you a simple example. Okay, one method is this. Sorry, I will have to close this. Okay, so what we have
Yes.
seen is xt. If you are giving xt as the input to a linear time invariant system having impulse response ht, the output is xt convolution ht. Okay. Now the question is how to find the impulse response of a system, because we cannot physically realize this impulse signal. There are different methods in practical cases. One possibility is that we can generate an approximation of this delta function. What is delta function? It is a very if we can generate, we have seen that it is a limiting case of this rectangular pulse, isn't it? If the height is 1 by delta and the width is delta, so if we keep on reducing the width, the amplitude will increase, and in the limiting case it would be a delta function. So we can say that it is a very short duration pulse with a very high amplitude, isn't it? So we can generate an approximation of that delta function, and there are some other methods. Sometimes we can find it theoretically also without actually generating that delta function and measuring the output. Okay, I will take one example. So let us consider an example. Have you studied this RC circuit in your this 291 course? Hello.
Yes, sir.
You have.
Yes, sir.
Okay. So this is RC. Let us consider a system. This is the input to the system, and output is this. Okay. And what circuit is this? What is it called?
The integrator.
This is called an integrator. Now, can we find this is the system, xt is the input and yt is the output. Can we find the impulse response of this system? What is the impulse response? We have to give delta t as the input. Can you tell me, if we are giving delta t as the input to this RC circuit, what will be the output? That means I am doing so what I'm doing is delta t as the input. What will be the output? Assume that the capacitor is initially discharged. There is no charge in the capacitor. Now, can you tell me what is the value of yt for t less than 0? T less than 0, what is the input signal? T less
is
than
0, sir.
0, it is 0, isn't it? Because the delta function is non-zero only at 0. Delta function is 0 for t greater than 0 and t less than 0. It is non-zero only at t is equal to 0. Is it? Now, can we say that the output of this system is what? For t less than 0? Is it yt is equal to 0 for t less than 0? If there is 0 input, capacitor is initially uncharged. So what is the output? Yt, is it 0 for t less than 0?
Yes, sir.
Yes.
Now what will happen at that instant of time? There is an impulse. That means the voltage across this is delta t. This is delta t, and then is it this? Now tell me, what is the output across this capacitor at that instant of time? What is the property of capacitor? You must have studied. A capacitor cannot, how a capacitor respond to a sudden change in voltage? It acts as a short circuit or open circuit?
Short.
It acts as a short circuit, isn't it? For sudden change in voltage, capacitor acts as a short circuit, and for sudden change in current, the inductor acts as a open circuit. You must have studied it in your circuit theory course. Now at t is equal to 0, can we say that this is the equivalent circuit? Capacitor is a short circuit. Is it that? Now what about the voltage across the resistor? What about the voltage across the resistor? Delta T is the voltage here. Let's say this is plus minus. Delta T is the voltage here. What about the voltage across? This is a short circuit. And what about the voltage across the resistor?
So delta T.
It must be delta T, because at any instant of time, KVL must be satisfied. Okay. If this is the voltage, that must, the drop across the resistor must be delta T. Now, what is the current flowing through this resistor? current flowing through this capacitor. If this is delta T, voltage is delta T. What is, and this is R, resistance is R. What is the current flowing through this resistor?
Delta T by R.
It is delta T by R. Okay, that is what is happening at T is equal to 0. Now what happens at T? What does it mean, 0 plus? Just after 0. What will happen to this?
It will be 0.
0 means what? Is it an open circuit or short circuit? 0 voltage means, is it a short circuit? Is it the circuit after 0 at T is equal to 0 plus? That means when the impulse, after that impulse strikes, just after that. Now tell me, what about what is the voltage across this capacitor at this instant of time? What is the voltage across the capacitor? What is the voltage? What is the equation for voltage across the capacitor? Is it integral minus infinity to T, what? 1 upon C into I tau d tau? Is it that? Is it the capacitor relation between the current and voltage in a capacitor? Is it that? Now my question is, what is the voltage across this capacitor at 0 plus? Is it 1 upon C? And what is the current flowing through the capacitor at T is equal to 0? Is it delta T by R? So is this the voltage across the capacitor minus infinity to, let's say, 0 plus delta? Is it that? Voltage across the capacitor? Now what is this voltage? What is this voltage? What is this integral?
1 by RC.
It is 1 by RC. It is area under the impulse divided by RC. Area under the impulse is 1 by RC. Okay. So at T is equal to 0 plus, this is having a voltage 1 by RC. Now for T greater than 0, what happens? For T greater than 0?
Decay of current.
It is for T greater than 0, this is a short circuit because delta T is 0. This is the circuit. So can we say that this capacitor discharges through this resistor? Is it that? Because the capacitor is initially at 0 plus, the capacitor is having a voltage 1 by RC. Now it discharges through this resistor. Is it that? What is the capacitor discharge equation? That what is the voltage across this capacitor? If it is initially charged to 1 by RC, what is the voltage across this capacitor? What is that? Is it Yt is equal to what? What is the
1
equation?
by RC
1 by RC.
e raised to minus t by RC.
This is for T greater than 0, is it? Now we can combine these two. Can we say that the output of the capacitor is 1 by RC e to the power minus T by RC? I am writing it as UT. Why I am writing UT? Because this voltage is 0 for T less than 0 and this for T greater than 0. So is it the impulse response of the RC circuit? What we have done here is we are giving an impulse as the input and trying to find out the output. So this is the impulse response of the RC circuit. 1 by RC e to the power minus t by RC ut. Okay. And don't worry about this, even if you didn't understand this procedure. This is just, I have shown that we can theoretically find the impulse response of a system. Okay, particularly these RLC circuits, we can find the impulse response of the system.